Here. Actually, why don't you come in front, John? I have something for you. Okay, welcome everybody to our annual Lucy Engle Undergraduate Research Symposium. This is our departmental biggest undergraduate research symposium of the year, and it was established actually many, many years ago, and in memory of John's mom, Lucy Engle. And if you look at the program, there's a page which introduces her life and her support of the education. That's why we named this undergraduate research symposium after her. And starting from so used to be, it's just a oral presentation, which you will experience for the first part of the program. About 2-3 years ago, we also added the poster session, which runs out very well. So after this oral part, we all move on to the lobbies. We'll have poster sessions, we'll have food, you can exchange physics in addition to other fun stuff you do in your life. Okay, without further delay, let's get things started. But before we start, I have two things to present to John. One is a very special program just for John. Not only have all the information you have, it also includes the thank you notes of the students, and on top of that, signature of the students. So if one of the students gets really famous in the future, you can sell that on eBay. Okay, thank you, John. And another thing is, for this year, we prepared also a special T-shirt for all our presenters, including and John. It's specially designed by Katie. The front look like that, and then the back has the name of all the presenters. So it's a special gift for all the presenters and to John. And now let me hand it over to David, and he will feature the session.
So we're going to go ahead and get started since we're a little behind right now. So I'm going to turn the floor over to Raj, who's going to do the first presentation. Go ahead.
Perfect. Hello, everyone. Today, my name is Raj. Today, I'm going to discuss how helicity operators in SCAT organize scattering amplitudes and how this connects to structure in gauge theory and gravity. The goal is not just to compute amplitudes, but to understand why they take the form they do. So, what is the big picture? Let me start with the overall structure. We begin with SCAT, which is an effective field theory designed to separate different momentum scales. When we construct operators in helicity basis and match to the full theory, the Wilson coefficients turn out to be directly related to scattering amplitudes. Once we look at amplitudes in this form, we see additional algebraic structures such as fluid kinematics duality, which in turn lead to gravity amplitudes. So, let me start with some formalism. So, where the spinor factorization comes from. For a massless particle, the momentum satisfied p squared is equal to 0. So instead of viewing momentum as ordered 4 vector, we rewrite as bispinor form as p alpha alpha dot. This form here. The massless condition implies that the determinant of this 2 by 2 matrix vanishes. So determinant p alpha alpha dot is equal to 0. So which means the matrix has rank 1. And the rank 1 matrix must factorize. So we write p alpha alpha dot as lambda alpha, lambda tilde alpha dot. In other words, a null momentum vector naturally decomposes into 2 spinors. The objects lambda and lambda tilde are 2 component spinors that encode both momentum and helicity information of the particle. Once this information is introduced, Lorentz invariance becomes simply products of 2 spinor brackets with ij this here. So instead of manipulating complicated tensor structures with Lorentz indices, which is why scattering amplitudes reduced to algebra of spinor variables. Helicity amplitude simplifies so dramatically in this formalism. Geometrically, this diagram illustrates the decomposition of a light momentum vector into a pair of spinors. Now we move to the next big question. How do we describe polarization? So polarization vectors can be written in spinor form, but they depend on reference spinor Q. At first, this looks strange. Why introduce something arbitrary? But the key point here is that change in Q only shifts the polarization vector by amplitude or momentum, and because amplitudes are gauge invariant, they're insensitive to the shift, so the dependence on Q is not physical, it's just a gauge choice, and the gauge shift I've written down here. So, little group scaling here tells us that how objects change under rescaling of spinors, definite helicity. The diagram meaning different arrows polarizations that differ by piece along p mu represent the same physical state. Now using these variables, tree-level amplitudes take an extremely simple form. This expression is known as MHP amplitude. From a Feynman diagram perspective, this would involve some many diagrams, but here everything collapses into a single compact expression. Uh, so this tells us that usual diagramming expansion is not the most natural way to describe such physics. At tree-level, amplitude simplified considerably. So this is much easier way to write down this one. So this is not apparent in a diagrammatic expression. Um, G here is the coupling constant, interaction strength, the trace that is multiplied by TA here. That's dot dot dot. That's color structure. The group theory part of QCD. AN is the amplitude of every particles, NH3 known as maximum helicity quality, simplest amplitudes, two negative helicities, rest positive. IJ, spinor products, and coding kinematics. Diagram meaning particles arranged in cyclic order, reflecting how color flows. Now we move to soft color vector field theory. Let me mention some of the people here. And these are all the people that are on visual speakers in the development yet. So, soft collinear effective field theory reorganizes the theory by separating momentum into components along light-like directions. We introduce two null vectors and we compose momentum accordingly. Different modes scales differently. Collinear versus soft. So, Q here is the large energy scale. Lambda is the small parameter approximation. PC, the PC that's equivalent to Q1 lambda lambda square. That's collinear particles, jets like. And this term here, that's the soft particles, low energy. Diagram meaning jets moving in different directions with soft interaction in the center. Now the issue is gauge invariance. So when we separate modes, um, we have to make sure gauge symmetry is preserved. This is why we introduce Wilson lines. Physically, a Wilson line represents the effect of infinitely many gluon emissions along a direction. So using Wilson lines, we construct a gauge invariant building block which behaves like a physical collinear gluon field. So Wn here is a Wilson line exponential of gauge field that returns many gluon emissions. Um, A and mu here, that's the gluon field. B and perp, that's the gauge invariant combination of gluon fields, diagram meaning a particle along direction n emitting many gluons weakly lined. Now, instead of working with many vector indices, we project onto helicity states. We define operators that correspond directly to plus or minus helicity gluons. Um, The key result is that these operators only create states of a definite helicity. So the operator basis is already aligned with the structure of amplitudes. Bi, this term here, that's operator scaling plus or minus helicity gluons. Matrix elements is equal to probabilities to produce a certain helicities. Diagram meaning filter that gives plus helicity and removes minus helicity. Now we are the central part. Central magic step between full QCD and SCAT. In full QCD, the matrix element gives physical helicity amplitude, which in SCAT, the same process is treated as helicity operators. This operator here. that's multiplied by Wilson coefficients. The tensors T bar K separate the color structure using SU3 generators. TA. Physically, the Wilson coefficients encode the short distance hard interaction physics, while the scat matrix elements certain contain the universal soft and collinear dynamics. Since scat already reproduces all infinite physics, the only information left in the matching coefficient is the finite hard part of the full QCD amplitude. This gives us the matching relation. The CK lambda is equal to negative IK IAK finite part, meaning that the Wilson coefficient is literally identified with the finite part of QCD helicity amplitude. The diagram summarizes this flow. The full QCD is projected through matching onto simpler scan operator matrix. So now here we look at concrete example of matching procedure using the 4-gluon MHP amplitude. We begin with the well-known 3L helicity amplitude for 2 negative helicity gluons and 2 positive helicity gluons. The remarkable feature of the spinor helicity formalism is that this entire scattering process collapses into a very compact expression, written only in terms of spinor products Engle IJ. Yes. So in SCAT, we then construct a helicity operator basis with the same helicity structure, namely O minus plus plus is equal to um, this right here. So the matching condition tells us that the Wilson coefficient associated with this operator is simply the finite part of the field QCD amplitude, giving this expression here. So we show explicitly here how a complicated gauge theory scattering process becomes encoded into a simple helicity operator multiplied by Wilson coefficient. Here we move to one of the deepest structures discovered in modern scattering amplitudes. Any Yang-Mills tree amplitude can be rewritten entirely in terms of cubic graphs. Even though the original Yang-Mills Lagrangian also contained a 4-gluon interaction vertex. The reason is that the 4-point vertex can always be algebraically redistributed into an equivalent sum of cubic diagrams by absorbing contact terms into the numerator. So the cubic representation is not a statement about the little Feynman rules, but rather about an organization of the full amplitude into a form where every term has cubic propagated structure. In this representation, each diagram carries three ingredients: a color vector psi, a kinematic numerator ni, and a propagator denominator is di. The colors factor satisfy Jacobi identities because they are built on the Lie algebra. So can be the algebra structure constants of SU3. The remarkable discovery is that the kinematic numerators can be chosen to satisfy identical algebraic relations. This is called color kinematics duality. Physically, it suggests that space-time kinematics secretly obeys an algebraic structure analogous to gauge symmetry itself. The symbol NS, those are known as the simplest kinematic numerators of cubic diagrams in the SS and U in STU channels. Diagram meaning 3 cubic graphs, STU channels created by swapping lines. Now, this is known as the double copy relation, which is often informally stated as gravity equals gauge theory squared, but the statement is systematic and should not be interpreted literally as squaring a full amplitude. What actually happens here is more precise. Once gauge theory amplitudes are in color kinematic satisfying form, the color factor Ci can be replaced by another copy of the kinematic numerator Ni. The resulting object then reproduces a gravity amplitude. So the gravity amplitude is constructed from a product of kinematic numerators diagram by diagram, not by naively squaring the full gauge amplitude. In the 3-point example shown here, the gravity amplitude schematically behaves like the product of two gauge theory amplitudes, which is why people loosely say gravity is the square of gauge theory. The Ni simply denotes as second copy of the kinematic numerator, which may come from the same gauge theory or from another one. Physically, this suggests that the gravitational interactions inherent in algebraic structure directly from gauge theory. Diagram meaning one gauge theory copies into another produces gravity. So let me summarize everything here. In summary, spinor helicity methods allow gauge theory amplitudes that to be written in an extremely compact and elegant form, while SCAT organizes this amplitude systematically through helicity operators and matching relations. The central result is that the Newton coefficients of SCAT are directly related to by matching relations. The central result is with finite QCD helicity amplitudes, and these amplitudes furthermore exhibit hidden algebraic structures such as flexibility, which ultimately connects gauge theory to gravity and color copy construction. We can expand this into three more structures. This is known as supersymmetry and superamplitudes. This leads to something known as Seiberg-Witten theory. Edward-Witten, the same Edward-Witten. Um, there's one more thing. You can take this into twisters and momentum twisters. That formalism as well. It becomes more geometric there. There's also something known as global formalism. Thank you. Questions?
All right, thank you, Raj.
My name is David Cruz. I work under Engle method, and this is simulating the best substitutions on molecular diagrams. So, in recent developments, technology has advanced to the point where we can essentially throw very small facts. This is mainly through the laser technique known as high harmonic generation. And what they are able to approach the scale of nanoseconds or 10 to the 18. And just to give you a good idea of just how hard this is, the ratio between 1 nanosecond and 1 second is around the same ratio as 1 second to the entire history of the universe. So this has many applications, just because nanoseconds are essentially on the time scale of electron dynamics. So for example, in photosynthesis, when light interacts with electrons, that's around the scale of nanoseconds. Furthermore, charge migration is around almost nanoseconds, maybe a few femtoseconds. So with this advances in experimentation, we need theory to help us practice, and this is mainly through theoretical simulations. So how do these simulations work? Well, first off, we start with Schrodinger equation for our system, which is going to be a molecule in this case. And just for a little guidance, the little capital R represents the distance between the atoms, and the little lowercase r is for the distance to the electrons. So we have our Schrodinger equation for the molecule. However, just to make things easier, we're going to start off by essentially turning the Hamiltonian and only focusing it on the electron. So for example, the kinetic energy of the electrons or the Coulomb interaction between the electrons. So using this electronic Hamiltonian, we're essentially able to get a Schrodinger equation for this electronic aspect. And one important thing to note is that the eigenvalue of BHA is known as the potential energy surface. And this essentially describes the distribution of electrons. So for example, this little diagram, we say that each electron is perhaps first excited state would be represented by this little curve, whereas this electron is excited state would be related to this. So using this electronic Schrodinger equation, we also have this little phi term. And this, along with a nuclear term, can be used to write just a basis for the wave function in general. And with this basis, if we plug it back into the original Schrodinger equation for a molecule, apply some mathematical trickery, we eventually get this equation. And this equation essentially tells us that the wave function is dynamics and determines that potential energy surface happens earlier. So the question now is how we get this potential energy surface. Essentially, we have a molecule, in this case we're using methyl iodide. We have some configuration of it. We ask the computer, okay, what's the energy of this system? It gives us a point. We then change the configuration, stretch some bonds, maybe bend them a little bit. In another configuration, say what's the energy? Gives us another point. We do this, we get some discrete points, and with that, we're able to fit a nice curve to get the potential energy surface. Now we reach another question, which is essentially, how should we stretch this molecule? And another related question is how many dimensions is this going to take? So for methyl iodide, a direct sort of diagram approach would be, well, each atom can move in one of the three cardinal directions. We'll just assign a variable for each of them for each single molecule. In this case, you can see that's 3 times 5, 15 variables. However, the problem with this is that it doesn't really acknowledge the fact that with this you have both translational and rotational symmetry. So for example, if I shift all the molecules on over to the right by say 1 nanometer, it's going to give me the same energy but for different variables. So we don't really want this because that's a lot of redundant numbers. So this is where normal modes come into play. Normal modes are essentially just a system of coordinates that are essentially just based off of the bending and stretching of bonds. And this gets rid of the redundant, 3 translational, 3 rotational symmetries, so we don't have to deal with 9 dimensions, which is pretty nice for what we want. This is additionally the direction way we stretch our molecules. So for example, the first mode is sort of stretching up and down between the carbon and iodine, and so we essentially stretch that to get our potential energy surfaces. And for methyl iodide, these are the potential energy surfaces that we get. These little bottom ones on the graphs are just the ground state for neutral methyl iodide, and these top ones represent the cationic states. So we calculated 4 representing the iodine p orbitals right here, and the 6 bonding and anti-bonding orbitals up here. These, however, we wasn't concerned with the p orbitals, which is why they're being small. So we have our potential energy surfaces now. But, what do we do with them? So we're going to essentially have a little ground state wave function, in its ground state, and then apply a laser pulse to it, which raises it up to the first 2 cationic excited states. And with that, we can then propagate it through time and figure out the dynamics. But we want some sort of way to characterize this. So this is where coherence has to be. Coherence is essentially the overlap of the 2 wave functions. So for example, in this case, there don't overlap, but in this case, high overlap, high coherence. I don't know. Movie here made by the graduate student taxonomists who figured out when they made this movie, because it's very helpful with this research just in general, and it should help, see coherence in real time. So for example, if you look at this one, will essentially be high coherence, they're going to be overlapped for pretty much most of it, and this one will oscillate between low and high coherence. So you can see it starts off with high coherence, and now it's getting lower coherence as the 2 wave functions high and low unit, and this continues. And then all these other ones are also their own mix between high and low coherence. So low coherence is nice. We want, to get something even better, we want ideally compare it with some other system. And this is where the isotope substitution comes into play. So we didn't just calculate the coherence for just methyl iodide, we also calculated it for systems in which methyl iodide 1.3 hydrogens are replaced with deuterium. And the reason with isotope substitution as opposed to something else is that it's essentially just affecting the mass of the system for each individual molecule, and not really affecting the charge or anything else. So we might expect some type of symmetry breaking because here all the masses are the same, and here 2 of them are different compared to another. Additionally, we might expect something to change about the normal modes because every mass is essentially hard to stretch those bonds. And with all these, you're able to calculate the potential energy surfaces of all the systems. They're all overlaid on top of each other. And with this, you can kind of get a rough idea of how, there are some changes, but they're like too drastic to the systems. So with that, we're going to calculate the coherences for all of our systems, which are up on the left. Just some things to note, all of the coherences are long-lasting for all these systems, and essentially they all have essentially the same main sine wave. However, what's different between the systems is that the plot one is different. And so truly, the difference between these, we have the Fourier transforms of all these coherences up on the right. And, just to point out, for example, one material is taking just that one main sine wave. However, this material has a lot of noise around it. So aside from also calculating the coherences, we also calculated the expectation value of the position operator for each of the modes. And this also represents, shows us a lot of information. For example, the 0 deuterium, 1 deuterium, and 3 deuterium, their third mode expectation value is all pretty sinusoidal. The 2 deuterium is a lot more chaotic with its, expectation value. Well, you might first think that this has something to do with the sync I mentioned earlier. However, if that was the case, you'd expect something similar to happen in 1 deuterium. However, that's not the case, which shows that it's something just beyond the sync which needs further analysis. So, in conclusion, we can now, with our advances, both experimentally and theoretically, look at these very small systems, very small time-scale systems. And while SLI does have long-lasting coherences, the isotope exchange only causes subtle changes to occur in the system. But for future studies, we can try to figure out a system and find one that has more desirable properties that has, perhaps a larger shift in its, the extended ionic states, which would cause a more drastic change. And I just want to acknowledge it once again to Max Thomas, who was very helpful with my research and my alignment. And thank you for your time. Any questions? Essentially, we're trying to find something with like some symmetries in it, but not like too complicated to deal with. So that's why I was just a sort of good overlap between that. Can you repeat that?
Can you extend this approach to molecules which have lone pairs of electrons? For instance, of methyl iodide, I go to ammonia, which has a lone pair of electrons. Can you use the same approach?
I believe you put something that's used for the approach. That's why I use the back version, so it should have a lot of areas.
But you don't find much. So you can say like that's on one side, and then you go to the other side. So it's inversion also can be taken care of. Okay. Thank you.
Any other questions?
Anyone next to that, Grace?
Hello, everyone. My name is Grace Gibbons. I work with Dr. Kanu Sinha and also with grad student Aaron Carlson. And today I'll be talking about Einstein's oranges, exploring light propagation, or the propagation of light rather, in media and gravity. Okay, sorry about that. So as we know, when light enters a media, it propagates into a medium, and the refractive index effectively slows the light inside the medium. And then what you might or might not know is that in the presence of gravity, light experiences a frequency shift depending on your space-time geometry. So the goal So the goal of my project overall is to determine how light propagates in a medium in the presence of gravity. So mixing both of the concepts together. So just more in-depth background of how the light is actually slowing within the medium. If you think of a medium as a stacks of sheets of dipoles, and you just look at that first sheet of dipoles and you have an incoming electric field, the electric field hits the medium and then it polarizes the atoms within the medium. So then the charges are wiggling essentially, which then creates a secondary field at the same frequency of that incident electric field, which then adds to our the original incident field, adding a shift effect the um, to the field within the medium. So then when we look at this, that's just talking about it with a single sheet. And then if you move to having a bunch of those sheets in a row, the phase shifts add up. And then moving from a discrete case to a continuous case, that's where our um, apparent slowing is coming from. So for the first model we were looking at, or deriving rather, was for a Lorentz atom, which is just where we model an atom as a simple harmonic oscillator. So you have an electron held to the nucleus with this spring. So to start our equations of motion, we have the first force is just the force on the electron from that incident electric field that we were talking about. And then the next force comes from the actual spring that we're talking about, with the omega naught as the characteristic frequency of that spring, which will depend on the atom itself or the material properties. So then there's also an effect from the quantized electric field. So if you start in a system with quantized electric fields, because even in vacuum you have particles coming in and out of existence, which creates electric fields. If you take a Hamiltonian of that and then you derive your equations of motion, you'll get this damping term. So it damps the actual oscillator itself. So then our goal is we're trying to find the polarizability from this. So we start with these equations of motion that I just went over, and then we solve the equations of motion for polarizability. And then we solve Maxwell's equations for the refractive index from that specific case. So now that was our model with just the Lorentz atom, and now we're looking at the Lorentz atom in gravity itself. So just a little bit of basic general relativity background. The object that describes the geometry of space-time in general relativity is this metric tensor. So in our case, we're just using a 1 plus 1 dimension, so we're using one spatial dimension and one time dimension. And also in our case, we are assuming that these the off-diagonal elements are 0. So that this G00 term it relates our proper time to our coordinate time. So from your relativity class, you might remember your coordinate time is just on the actual coordinates, and then your proper time is from the observer on our coordinate. So from before, this is our equation of motion with flat space-time, just in your general case. And then this is our expected equation of motion in gravity. I'm currently working on this calculation. But this just goes to show that this redshift factor relating our proper time to our coordinate time is showing up in each of the different force terms. So then for the future work, for what I'm working on after this, is to continue this calculation. So finish solving that equation of motion, and then solve the source-free Maxwell's equations in the space-time to determine the field propagation in gravity itself, and then finding the effective polarizability from that of, or find the effective polarizability of the atoms in gravity from similar to that first calculation that I was doing, except with gravity. And then I put them together and find the secondary field and its interference with the field by itself to find the interplay of the gravity and the atoms. So, in summary, I derived the polarization of an atom in a medium with an incident electric field, and I'm currently working on deriving the polarization for the same case but in gravity. And my future work is to model light propagation through both media and gravity together. Thank you.
I just wondering what the calculation was that you had in mind, or something for slowing down.
It's for, so based on our assumptions, we're using weekly like weak gravitational fields. It's actually background for Aaron's project specifically, but yeah, it's a we assume that it's there.
So, no doubt you're going to get a result, right? But then, how are you going to validate that experimental? Any observation done somewhere, anywhere?
I would have to think about that.
Any other questions? Thank you, Chris. Thank you, Chris. Up next, we have Julie. Right. Good afternoon. Today I'll be presenting train or trees jet algorithms to use mathematics. Very long title. So let's get into it. So I'll start off with an overview of the standard model of particle physics. Specific ones we want to be interested in, or interested in for this, is the Higgs boson, W boson, top quark, and bottom quark. Higgs boson being, of course, one of the main central pieces as we look at, and it confirms the model for how most particles move with respect to mass. The W boson being the weak force, and the top and bottom force being the heavy forces of the up and down quarks that make up our protons and neutrons. So, specifically, we're interested in the top case, where the top quark tends to decay to the and the W boson, and the W boson then further decays into two jets, which are light quark jets of up or down. Higgs can decay into two B jets, or specifically B and TB. And as previously stated, the Levy boson can decay into two quark jets like this. So, how we study these things are actually through high energy collisions at the large hadron collider. Specifically, we're looking at the LHC, or the, as stated, Atlas detector. So, Atlas detector, a toroidal LHC apparatus, where protons collide, their products go all over us. And we detect it in this one tube. So, currently, the run rate, which is usually in like about a month, if I remember correctly, they have about 13.6 TeV collision energy on these collisions. And just for reference, the mass of particles are usually in GeV. So it's a very high energy compared to what our particles usually are. So we're actually studying these particles tend to decay very quickly. And from these decays, we have quarks. And these quarks actually give us these jets in our detectors. Think of it like this. We're colliding two particles together, and it's spreading out all of this stuff. For a more violent example, think of it kind of like a car crash. A car crashes, hopefully with nobody inside, and the parts spray all over the place, and you can see what the fundamental things are that make a car. Obviously, we're not studying cars here, we're studying particles, so we collide particles instead. So the Higgs and top are no exceptions. They're unstable and don't live very long. So we have to look at their decays at to quarks to actually study them. So the top decay for the Higgs is the two B quark jets, and the top can decay into two quarks and two quark jets and the B quark. And it's actually the most common one that we see. So looking at these, how are we actually what are we actually studying? Specifically, what I'm looking at are the resolved jets, or not the resolved jets, we're looking at the boosted. So when a particle decays, in its reference frame, it's shooting stuff out like this. But because of relativity and the very high collision, something's going very fast, very like these high energy collisions, these jets actually tend to smush together, as seen here. Picture this thing going like this going like this. For those who can see me, like this. So this large radius jet is a result of these two jets smushing together and overlapping. So when they're not very fast moving, we'll get these all jets, and they're very fast moving, we'll get these large radius jets. So, cool. What does it have to do with this project? So we're looking at the Higgs decay and the top quark background. So the Higgs, again, decays to two B jets, and sometimes they resolve the jet overlap and make this large radius jet. So that's what the Higgs looks like for this large radius jet. And we also have, remember, the top quark, which is our heaviest particle. And this has two quark jets right here, and this B jet, all overlapping into this large radius jet. Sometimes the B jet decides that it kind of hates the lighter quarks, so it just doesn't overlap with those, and that's fine. Although partially contained, and the other ones, the ones that have all three of them in this large radius jet, they're fully contained. So this is kind of a pain if you're looking at these individually, and obviously, if we're looking at these things closely, nobody's actually sitting there and being like, I think this is a big boson right here. So how do we actually distinguish these things? Well, the thing I'm looking at here is an ML algorithm. So this the top word background is actually distinguished by this ML algorithm. And that's not supposed to look like that, but cool. Alright. So now our algorithms are very complicated. AI is kind of they behave and you have to correct them. But in this case, it's behaving in a way that it's learning how to look at distributions of mass like this. So for our background, we have this mass distribution of these two events. We have the fully contained over here, and the partially contained in this code. And as you can see, this distribution actually shows the full complement. We have this 175 GeV, which is corresponding to the top part mass, and this small p that is corresponding to the W boson mass from this W boson fully contained. Cool. So obviously, we're not going to get this. The first thing we're going to look at is look at this type of graph and be like, okay, so this peak right here, obviously it's upward. Don't want that. So when training these algorithms, we actually go from here to here. So this is done through resampling. What we do is resample for the smoothness to look like this distribution over here. And this distribution is just a unphysical case mass distribution. The reason why we want this to be done is when we're looking for the Higgs, we don't want it to learn, oh yeah, 125 GeV and look at just the distributions. So we give it this unphysical data set to learn what the Higgs is by looking at text. But when we have the top word background, we have to make sure that the top word background looks similar to that. Otherwise, it's just going to learn this top word, this Higgs. So, an example actually looks more like this. And there's a slight problem here where there is this partially contained having a peak over here at the boson mass. And I'll explain that in a bit why that's a problem. Actually, right now. So, G3S, our algorithm, with the standard pre-processing, in other words, the way how we resample these data sets into the training sets, is fed into a trainer, and this trainer gives us our algorithm. Now, if we want to evaluate how it is correlated to mass, we want to make something like this over here, where we have these bins of mass separated, and these all have this column of this score over here, of this ML1 score. So, one being, oh yeah, this is the top part, and 0 being, of course that's not the top part, what are you talking about? So, if you take these mass bins and normalize them, you can actually get this score, and it'll be the most likely, or it'll be the higher probabilities of this score being high, and 0 just being, no, that's not seen. So when we take this, this is kind of hard to look at. So what we're going to do is we're going to look at these different mass bins, and we're going to put the particulars mean of these bins and plot them. So over here we have the mean normalized value of these bins, and we have the mass. What's familiar? So that's not supposed to happen. That is straight up the distribution, which indicates a strong correlation between mass and the score. And ideally, this graph right here would be a flat line because this is all top part of the case. So in other words, it shouldn't be learning, oh, this is right here, mass 175 should be the top word. It should be a flat line being, okay, these are all top words, ideally. You don't live in this ideal situation. So what we do instead is we're going to change how we give this data set. What we're going to do is we're going to change the pre-processing classes in our pre-processing class software and give it, instead of this being the top portion case of partially and fully contained all together in this top class, what we're going to do is we're going to take away the partial and give it to WQQ. This is going to now be its own separate class, and the top part will contain is going to live by itself. It's a happy arrangement. So to compare a bit more in detail, this is the graph we get now, where we have this fully contained and this other from top being the same distribution, but there's no partially contained and there's no peaks. So in theory, we should see that this thing doesn't learn the W boson mass peak, as it can probably distinguish this set between this and this set because of this. So let's compare them. Our results give us this P, this type of preprocessing, and our results using this preprocessing give us a Y. So it's still learning how to do math. So for the current conclusions, it's kind of inconclusive as our P's not flattened, and this might be due to some physical reason, but that is still a matter of further investigation. And what I propose, we can actually punish mass dependence in the loss function of these trainings if we want to see further reduction. So with that, I'd like to give a special thank you to Dr. Heinemann, Dr. Schwartz of the University of Arizona Physics Department, the University of Arizona HPC, Atlas Collaboration, the University of Chicago for their analysis facilities, and their program who started me on this project in the summer. Thank you.
I'm wondering what type of algorithm it's like. Is it like a graph algorithm?
It is a transformer neural network. That is the architecture we're using. GM3X is the newest version of that transformer neural network to learn this type of tagging. And like it's going to be tagging if it's top or background and what the different depths should be.
Yeah. And also, I have a quick question. So, are you using any type of like variables in the loss function right now?
Okay, the loss function is based off of a bunch of different factors, such as the actual momentum of the jets and some of the other factors that are currently disappearing from my head. I do have them on the write-up I did for this, but it is using a bunch of different variables. And I do believe that says that this ends up having a bunch of variables. I do not know the exact numbers off the top of my head.
Is mass the only feature that you have to work with?
So mass is not the only feature, but we don't have to learn mass because it biases how we do our analysis for these data-driven backgrounds. So when we're looking at the data, we want to make sure that that our background is data-driven, as that's how it's done for tablets at least, and future CMS. So when we're looking at these data-driven backgrounds, our data-driven backgrounds can actually be biased by this mass selection of the jets. And sometimes the jets aren't constructed by this or CMS, so that would also be a problem to just have it being biased on mass. So mass is the more important on these of this algorithm.
Any questions? Yeah. Alright. Thank you, Julio. Up next, we have Jorge.
So, good afternoon, everybody. I'm Oscar Redondo. I do research at the Student Observatory and Enterprise Telescope Research Group under the supervision of Dr. T.J. Chan and the disaster of much. Today, I will talk about how we model black hole spectral energy distributions using a biased multi-column model. So, almost all galaxies host supermassive black holes in their centers, and many of these black holes are actively creating matter and thus emitting radiation in this process. This multi-wavelength radiation can encode a lot of properties and information about the black holes and their environments. So, for example, up here, we can see the first ever image of a black hole, Sagittarius star, taken by the Horizon telescope. And here we can see a spectrum of a simulated GRHD simulation of this Sagittarius star black hole. And we can see that it includes information from all the electromagnetic spectrum. So what of radiation is being emitted from these black holes? So we have three main types. The first one is synchrotron emission, which happens when the free particles like electrons in the plasma of the accretion disk uh, follow the magnetic fields inside around the black hole, sorry, and they spiral around them, thus emitting radiation. These photons then interact with the electrons in the actual plasma around the black hole, thus exchanging some energy with them. And finally, that is called Compton scattering, sorry. And finally, we have Bremsstrahlung. And Bremsstrahlung happens due to the interaction between the plasma itself. So this happens when electrons from the plasma are deviated or deflected by the nuclei of heavy atoms in the accretion disk. Therefore, they change velocity, thus changing their energy, and thus have to emit a photon to get rid of their excess energy. So the actual process of Compton scattering around these accretion disks is different from normal Compton scattering. It is called inverse Compton scattering. And this is because when a photon collides with an electron, these electrons in the accretion disk are traveling at relativistic speeds. So therefore, the electron has much more energy than the photon. Therefore, the photon gains the energy of the electron and is pushed to higher energy levels if the electron is decreasing its energy. So we can see here, for example, the blue line in the spectrum is synchrotron emission. And the orange line is Compton scattering, and the pink line is Bremsstrahlung, sorry, the purple. So we can see that Compton scattering has much higher energies than synchrotron emission because they have the energies of these photons have been pushed up. We also can see that Compton scattering has low luminosity because not all of the synchrotron Compton scattering. So how do we model these radiative processes? The code we use at HDU is called IGR It is a Monte Carlo radiative transfer code that is used to calculate the spectra of these hot, optically thin, radiatively inefficient plasmas. So radiatively inefficient means that the accretion disk is very hot and emitting a lot of radiation, but it is so optically thick it affords certain wavelengths that the radiation is hard to escape. Therefore, all the radiation stays in the accretion disk, or the vast majority of it, and we can examine it in these situations. So what the code does is it takes GRHD snapshots of general relativistic magnetohydrodynamics. These are the simulations of the black holes at their current state, and they use general relativity and create a spectrum of these simulations. So it shows the three peaks I explained before. So normally, you would have many billions or trillions of photons orbiting around these black holes, but the code obviously cannot keep track of all of them at the same time. So it uses the concept of superphotons. So let's take, for example, a magnetic field here that emits a lot of photons. What the code does is it creates a photon, superphoton, sorry, with a weight, which is the number of photons it has in it, that is much greater than 1, and it gives them all the same space-time position and wave vector. So it groups them onto a packet and then just propagates them along their geodesic and keeps track of them as they move using VR. Radiative transfer is used to account for attenuation and scattering and emission. I would also like to point out that a Monte Carlo method, this is what the Monte Carlo method comes in because it is used to determine where the photons appear and with what energy they appear. So how does the code deal with Compton scattering? So when a superphoton encounters an electron, two things can happen, or two things will happen actually. Part of the superphoton will go by undetected, undeflected, sorry, and some of it will interact with the electron. So how we measure how many of the photons inside the superphoton will interact is using a very important parameter called the bias. So let's take, for example, a superphoton with a weight of 10 to the 6, so 10 to the 6 photons in the superphoton. If we have a bias of 10, the undeflected photon will have a weight of 9 times 10 to the 5, and the scattered photon will have a weight of 10 to the 5. So very few photons in this superphoton will be scattered by the electron. This is because electrons are really small particles and thus have a really little cross-section. So this brings in the ratio, which is the number of superphotons that are created through scattering over the number of superphotons that are created through emission. So ideally, we would want a ratio of 1, because that would mean that if the ratio is much smaller than 1, scattering will be undersampled, and we will have a very histogram-like picture at high energy, very noisy. if the ratio is much bigger than 1, we will have an uncontrolled chain reaction, very similar to a nuclear chain reaction, where a neutron collides into a heavy nucleus, then produces more neutrons, then collide into more nuclei. Well, this is the same, but with superphotons and electrons. Superphoton will very few an electron, just produce more superphotons. This will become very computationally heavy and cause a proton to crash. So, as examples, here to the left you can see, so firstly, these are two simulations of the same black hole, Sagittarius A star with the same conditions. To the left, we have one with a ratio of 0.17, so a small ratio, and to the right we can see a ratio of 1, which is what we were looking for. We can see firstly that confidence pattern here is much more histogram-like, unlike the smooth grid that we can see with a ratio of 1. And we can also see all these green lines here. And this is double confidence scattering. So this happens when a synchrotron electron is travels through the plasma, scatters and is quantized once, and then scatters and is quantized for the second time. We do not see this when the ratio is 1. So this is clearly an effect of having a too low ratio. So my task in this research group is to produce a library of different scenarios for different conditions of the black hole. So for example, different masses, different accretion disk plasma mass densities, different magnetic field strength, different spins. So looking at masses, for example, I'm testing everywhere from Sagittarius A star mass to the mass of the black hole M87 star. One of the main things I found out is that bias scales with black hole mass. So for example, let's take a black hole with a mass of Sagittarius A star, and we give it a bias of 256. This will give us a ratio of 7.2. If we take the same, if we take a different black hole with a mass of M87, and we give it the same ratio, the same bias, we will have a ratio that is basically 0. So therefore, in order to get the same ratios with different masses or different conditions in general, we will have to change that bias. And my job is to find the correct bias for each case. This project will make SED calculations much easier to work with. And some of the applications, some of the most immediate applications are using it for the current ongoing M87 movie campaign that the EHT is producing right now. So they are examining how the accretion disk and how the magnetic field of the black hole M87 changes over time. So you can see 3 snapshots of M87 at different years. And also using it to model AGNs after galactic nuclei. So AGNs are the supermassive black holes at the center of galaxies, which have really bright accretion disks, and they can also be studied through these processes. Thank you so much for listening. Any questions? Yes?
In the previous slide, are there other parameters that can be used other than the mass to get a good ratio?
Yeah, so we will test parameters, for example, like the mass density of the accretion disk of the black hole, or the magnetic field strength, or different spins of the black hole. So we're trying to look at every case of black hole that we can have, essentially.
Right. Thank you.
Test.
Okay.
Awesome.
All right. Thank you, Mario. Thank you, Captain.
All right. Hello. I'm Henry, and I'm going to be telling you guys a little bit about what I spent last year doing at NSF NORLab across the tour. So I'll start with a little bit of motivation. So time as an astronomer is really hard to come by. You essentially are always limited by how many people want to use your telescope. What is the scheduling of that telescope? Is there someone else who's running some big project at the same time? And this is really complicated by things like TESS, the Transmitting Exoplanet Sky Survey, which explored 85% of the sky detecting 8,500 candidate exoplanets by the transit method, which we'll talk about in a second. And so far, we've only been able to follow up on about 800 of those, simply because we do not have the time to spend observing 8,000 exoplanets to follow up on all of them. And so, the motivation for this project is we want to create a scheduling algorithm that is maximally efficient, using information theory and some statistical approaches in order to get through TESS and other similar sky survey backlogs as quickly as possible, such as Kuiper. There's also this other problem, the uniform observation problem. So in the past, the gold standard for observing schedules was the in-quadrature survey schedule, where you observe the planet when it makes a 90-degree angle with its host star in your line of sight. But this was shown by Dr. Jennifer Berg and Engle in 2018 to actually bias your data. And since then, astronomers, exoplanet astronomers, have been in a bit of a scramble because we don't have a standardized observation schedule that you can just use, which leads to people just observing what they can. Really quickly, we're going to talk about how we detect exoplanets. There's two primary methods. There's the radial velocity method, where you detect the Doppler shift of the star from the angle that is enacted on it by its planet. And then there's the transit method, where you see the actual influx from the host star from the planet passing in front. So, we want to find a way to quantify the information of the National Planetary System as a function of time, and then use that to schedule future observations to arrive at a fitted model. And we want to do this specifically for test data, which is collections of transits. So, these so-called, this information scheduling strategy is called maximum entropy sampling. And methods have been theorized for radial velocity signals, specifically in 2008 paper. Even though it's been 2 decades, no one has computationally implemented them. So that means if we want to work with test data, we have two big steps. A mechanism to create a guess at the orbital parameters from the transit light curve, and then taking those parameters, creating hypothetical RP signals, and then implementing maximum entropy sampling methods as hypothesized by the 2008 Ford paper, and seeing if we can converge to a fit of orbital parameters faster than other scheduling algorithms. So, for the sake of this project, we're using a model system of a orb Jupiter, which is something around the size of Jupiter, around a star the size of our sun, that orbits within 180. In this case, it's about it's 0.280. Yeah. So that first step is called rejection sampling. So from that test data, we only usually have one transit, one dip influx. And so what that means is we are very limited in what information we have about the system. We have a guess at the star to planet radius ratio, and we have a rough guess at the period by assuming that it's circular and using the ingress and egress times. But the most valuable thing that this test data gives us is a metric of comparison. Because with these rough guesses, these rough priors on the radius ratio and the period, we can iterate over every single possible combination of eccentricity. How elliptical is your orbit? The argument of periastron, the orientation of that eccentricity relative to your line of sight, the orbital period, and the radius ratio. And then we can systematically compare all of our models to our real observed data. So, for our warm Jupiter system, these look something like this, which is sort of just a jumble of colors. But you can clearly see these deviations in radius. These are radius ratio iterations that are changing how much flux is blocked from the host star. And you can see that the duration of the transit changes with your period changes. And so, what we're going to do is we're going to compare all of these generated light curves to each, with a set of model parameters, to that tiny, small snippet of known test data. And so we do this by log likelihoods, which we're not going to get into. But this is interesting because light curves have a lot of degeneracy. So a lot of orbital models with very different parameters can lead to similar looking light curves, just by sometimes the period is faster or slower in this case. You can get a similar looking period to if the eccentricity is larger. So by doing this, we can select the most likely sets of model parameters from this batch, and then because we have all the model parameters, just create hypothetical light curves with the constraints we would put on our system. And so, in our case, that looks like this, which I know this is very hard to read, but just so you can see that there are these long period orbits that have low amplitude, and there are these much faster orbits with much higher amplitude. So you can see that degeneracy of cases in that all of these produce a light curve that is similar enough to that initial snippet of test data. So now with that set of RV models, we can move into the actual maximum entropy sampling. So we use this formula for what's called Shannon entropy. I'm going to break this down real quick. This is important. So essentially, this first term, not first term, this last term, this long term, inside the nested integral, essentially says how expected is any velocity when you consider every model. So you sum over this dummy variable of models, and it asks, it returns a function of velocity for how unexpected that velocity would be relative to every model. Then you have this first PMT term, you can see that, this first PMT term. What that says is it weights this Shannon entropy by the probability of your model given your data. So essentially, how likely that model is informs how much we weight it in our entropy calculation. And then this last term says, what velocity does each model predict? So when you take that product, it tells you for each model how surprising a measurement of v. So then when you integrate over every model and every velocity, you get one number per time that tells you how shocked would I be averaging over all my models to measure this velocity. And so what that looks like in a simplified case, so all of these orbits have the exact same period, is something like this. So you can see that the entropy peaks when the models are the most disparate, essentially when you would be most surprised relative to each model to measure something else. And you have the least amount of entropy here in these sort of chords, because if you measure something smack dab in the middle because there's some measurement noise on your signals, these are all sort of enveloped in that. That doesn't really tell you anything compared to measuring here. And looking at a little bit more of a complicated system, you can see that the entropy curve is a little bit more calculated. And you can see what I'm talking about in selecting the significant peaks at which to sample. So here we selected the first significant peak, and this will be our new sample. So this is how we're going to optimize our scheduling. We can pick observations where the entropy has a significant peak, because these are definitionally our most valuable observing times. And then after we take that measurement, we redo the entropy calculation, choose a new peak at which to sample, and go on until we have enough data points to fit with an orbital fitting model and get a good guess at the parameters. So, just a quick note, for any time you do a follow-up observation, you need 3 preliminary observations first, because otherwise you don't know if that influx could be from something like wind darkening or just random star variations. So every single time you do a follow-up observation, you have to do 3 preliminary observations to confirm if the planet exists at all. So after these 3 preliminary observations, we can then test our maximum entropy sampling method against uniform sampling and random sampling. Uniform sampling is, as it sounds, you take an observation with a cadence of once every week, and random sampling is you pull your separation of samples from a distribution between 3 and 10 days. So, maximum entropy sampling for this warm Jupiter system converges in 3 to 4 additional measurements from your 3 preliminaries, so 6 to 7 in total. Whereas uniform and random sampling both take 4 to 6, on average 5 or 6. The 4 depends on sometimes the random sampler gets lucky and sort of just lucks into guessing the same observation that the maximum entropy sampler does, but it is a possibility. And so what this tells us is that maximum entropy sampling works. It creates a statistically significant change in how much time you need to spend observing. On average, 2 to 3 observations, which in the scheme of things is a lot. That's a 25 to 30% reduction in how much telescope time you're using. But the really promising thing about this probably isn't even as good as it can get. This sort of marginal benefit that we get from warm Jupiters is will be heightened when the signal to noise is worse. Because in this case, with the warm Jupiter, because the planet is so massive and so close to its host star, the radial velocities it's imposing are very large compared to your uncertainty, compared to your spectrograph's random noise fluctuations. So if we want to measure something like a super or a sub-Neptune, something of that variety, we will see with worse signal to noise that this method actually should get substantially stronger. And that has a lot of applications to extreme precision radial velocity. I'm going to spend the summer at JPL working on this with Dr. Jennifer Burke, who I mentioned earlier. Essentially, in preparation for the Habitable Worlds Observatory, which is NASA's next flagship mission, all of the preliminary observations that go into HWO, they want to do them with this sampling method. And implementing this for sub-Neptune and super-Earths to hunt for potential candidates. That is the end of my presentation. Thank you for your time.
So it's a spread of models that would make calculation coming from the data that you already have.
Yes. So essentially, we are comparing which. Wait, your question just
So
makes sense.
it's a spread of models that go into the calculation coming from the data that you already have.
Yes. So essentially, we generate iterating over all of the line curve parameters into a model. Some like hundreds of thousands if running on my laptop, millions if I get to run it on the Borderline cluster models. And then what you're doing with those is then you compare those to the singular transit that you see, and then you take, say, the 3,000, 5,000 most likely models, and then you convert those into radial velocity signals, which works because you already have like a dictionary of parameters that you use to define those transit signals. Does that answer your question?
Yeah. But so the question that I really had, I was making sure that I was understanding correctly, because the question that I really had is, well, why do you expect the gain from this sampling to be higher with lower signal to noise? I would have expected that with lower signal to noise, you just don't know what your model is, and so if you don't know what your model is, you don't know what to look for.
Sure. So I'll return to this slide. So typical RV uncertainty is within like 5 meters per second to 1 meter per second, depending on the spectrograph that you're using. And so you can look that even if the uniform sampler samples somewhere in this coordinate band, there's still a spread of about like 25 meters per second across this range. So if you're sampling with 1 meters per second precision, even if you observe somewhere in that range, uh, you're still going to discriminate a bunch of models out because comparatively, this is still a large spread relative to your uncertainty. But if you're dealing with a smaller planet around a like a sub-Neptune or a super-Earth, what's going to end up happening is these models are going to predict closer velocities because they're inducing less velocity on their host star, right? And so what that means is that this might only have 10 meters per second spread or 5 meters per second spread. So as like your spectrograph having 5 meters per second or 1 meter per second of uncertainty eliminates a lot less models, which makes it comparatively more efficient to sample here, where you can discriminate a lot more models with the same observation. Does that make sense?
Sort of, but I can catch up.
Okay, awesome. Any other questions?
All right, thank you. All right, thank you, Henry. Next we've got something.
Thank you. Hi everyone, I'm Sarah, and we'll be talking about the project I did with Professor Gall on black-hole Weiser effect and singular extreme quantities. So in an introductory course on general relativity, we learned that the event horizon of a black hole is a smooth linear hypersurface that is following the observer.
observe any divergences or any pathologies. But it turns out that for extremal horizons, that's not exactly the case. So we will be analyzing extremal churning and black holes. Churning black holes are black holes that are charged and spinning. They have some charge Q and some spin parameter A. They're going to be extremal, meaning that they have the maximum allowed amount of spin and charge given by x equals q2. And since they're spinning, they have a horizon angular velocity given by omega h. Now, these extremal horizons develop a additional symmetry called scaling symmetry that's not present in the non-extremal black holes. So, first of all, extremal horizons have developed this long infinite throat, meaning that the proper distance between the horizon and some point outside of the horizon goes to infinity as you approach extremality. That's seen in this infinite throat here. And you want to zoom into the throat by taking this lambda parameter going to 0 to get this, this coordinate transformation. We have a time parameter v, we have some radial parameter r. We will be moving into late times by multiplying v by lambda and taking lambda to be 0, and while we will be going very near to the horizon by dividing by lambda this radial parameter. Now, a generic tensor T will be self-similar in this coordinate transformation if it gains this lambda to the W weight, and here the W is just the scaling weight. So we will be analyzing perturbations using this scaling symmetry. Now, first of all, the black hole Meissner effect. This has nothing to do with the superconductor Meissner effect. This is just when they discovered the Meissner effect in the 1970s for black holes. Basically, the idea is that if you send in electromagnetic perturbations that are axisymmetric on the extremal Kerr horizon, they will be deflected by the horizon, so there will be no penetrating flux. Now, we rederive this using the scaling symmetry. It turns out that these axisymmetric perturbations for electromagnetism will have positive integer weights, W equals 1, and therefore the Maxwell tensor will have these components, and horizon is at R equals M, so on the horizon, the tensor is going to vanish. That's the deflection. And we also find that there's an analogous gravitational Meissner effect, where gravitational perturbations will have scaling weights W equals 2, and therefore the metric perturbations are pure gauge on the horizon. Now, another set of perturbations that are important here are photon or synchronous modes. You can think of these as perturbations that are caused by a charge or a mass that is moving with the same angular velocity as the horizon angular velocity. In frequency space, these are given by omega equals m times the horizon frequency. And we will be analyzing these using the Tarkovsky equation. And the perturbation parameter is these bioscalars, psi sub s. And if you solve these in the near horizon region for extremal Kerr black holes, they will gain these two power laws in x, where x is the distance from the horizon. So importantly, we have h minus 1 minus s and minus h minus s, where h is the conformal weight given here. Now, for axisymmetric perturbations, these conformal weights will be positive integers, as we said before, and one of these branches will blow up while the other will remain regular. So each one we denote one as non-physical, and the other one will give us the Meissner effect. However, for non-integer, for synchronous perturbations, these will be non-integer for these principal branch of perturbations, where the term of this root will be negative, so we will have h equals 1 half some I delta. So for these modes, if you go back to this equation, and ignore the s parameter here, you'll have h minus 1 and minus h. Both of them, since h has real part 1 half, will be minus 1 half. So we have two powers of x that are both minus 1 half, meaning that as we take x go to zero, they will both blow up. So immediately one would think we have a horizon singularity for these synchronous perturbations. Now, the careful way to analyze this is using the method of matched asymptotics. I'm not going to go over the mathematical detail here, but basically you solve the equations near the horizon and solve the equations in the far region and take basically match these asymptotic solutions in the middle to get the returning Green's function here. And when we do that and we take the synchronous limit, k goes to 0, we see that the Green's function goes up, g goes to infinity. So we do indeed get a horizon singularity for these modes. But the question remains that can these modes actually be physically excited? And it turns out that for pure black holes, for extremal pure black holes, that cannot happen because extremal pure black holes do not have time-like synchronous orbits. Synchronous orbits will be space-like for Kerr. However, for Kerr-Newman black holes, so if you just add some charge, there is a range of parameters for charge greater than or equal to the square root of 3 over 2. We indeed have time-like co-rotating orbits. So the next task is to do the same calculation for extreme alternative black holes where these modes can be excited. Now the problem is that in Kerr-Newman black holes, the perturbation equations are much more complicated, mainly because the black hole is charged, gravitational perturbations and electromagnetic perturbations are coupled. So here we will be working with two perturbation fields, both of them in Miles scalars. Psi minus 1 encodes the electromagnetic perturbation, psi minus 3 encodes the gravitational perturbation, and they will form this stronger scalar coupled second order ODE. These are all second order differential operators. And they will be using a near horizon consult. So that would be some power of r to the p times some angular function times 1. And the similar consult for the other one is power of p plus 1. I'm not going to go over the details of the numerical methods, but it's all numerically to find these power law, these exponents p and the angular functions s. These are two of the functions that we find, and we define these principal modes for the Kerr-Newman black holes. So we find p equals 1 half plus some imaginary term. But they are not present for the entirety of the parameter space, as we expect, because as we increase the charge, you will approach extremal white and non-zero black holes, but as you decrease the charge, you approach extremal pure black holes where you do have these modes. So under this blue curve over here, you have principal eigenvalues or principal modes. Of this, you don't have any principal modes. But as we remember, these modes are only physically sourceable, and the black hole charge is greater than square root of 3 over 2. That's the scoring right here. So there's this small strip of the parameter space where these modes exist and they are physically sourceable. So this is where we find our physical singularity. And the next question is that how does this singularity actually look like? So to do that, we use the QD deviation equation. So we take some infinite observer with some velocity u, and the deviation or deviation vector a from u is just the distance between the components of the system to this black hole, and the equation here is the and if you algebra here with the virtual space-time, you will find that in the transverse plane of the incoming observer, the geodesic deviation eta plus is going to diverge as you approach the horizon by this power of minus 1/2. So tau is amortizing the curve as tau goes to 0. This transverse relation is going to diverge. And at the same time, there's going to be an infinite amount of rotation for these geodesics as you fall into the black hole. So if you imagine this equation as just taking a ball of dust as it falls into the black hole, it's going to rotate infinitely, it's going to get stretched and it's going to stretch. So in summary, we analyze the perturbations on singular we analyze the perturbations of extreme black holes. Use the scaling symmetry. We find that for positive scaling base, we have the screening that is the binary bit, and for synchronous modes, we have non-integer base that is that gives us the singularity on the horizon, which gives us a anisotropic singularity on the horizon, which is very different from the particle to explosion singularity that we usually found at a simple level.
Thank you. So at this point, no presentations. I would like to stay here for just a second. We have a special thing we want to do. These components presented both your talks and posters that are on the picture down here. All right. I'm going to turn over to
Yes, hello, and I'm actually not about our students. And we have a special recognition for one member of our department. That is Christy. So Christy has been with us for only a little bit over a year, but it feels like she has been with us for a long, long time. And she has just been such a big support to our students in all the aspects, academics, other things, the time staff, and the enrollment, includes retentions, and all of those. It has been a great, great support. So it's great to have her as a dear party. And but on the other hand, she is leaving us, unfortunately, in physics. I mean, she will still be staying in higher science, working in her other roles. So I would like to present Chris a little present from the department, and thank you really to have you with us. It's great. A crowd which our faculty and the staff members have write some nice words over there. Sorry, students, we didn't have a chance to pass it over to you guys. You feel free come up to Chris and say all the nice words about her. Thank you. And this is the first time we have a physics mug. So you are the first person to receive our physics mug. Thank you. You're the one that knows Chris the best. You want to say something?
First of all, I want to say thank you for Christy for joining us. Definitely during this period where enrollment in undergraduate has gone up so far, that it was nice to have someone helping with me. So thank you so much. And I know that you're going to do great and fantastic over with neuroscience. So congratulations, and thank you for being a part of our team.
Okay, so the first part is officially over. All the student presenters and the poster presenters, please stay over, focus on photos. Otherwise, for the rest of you, feel free to move out. That's